Hello, my name is Jonathan Apostle, and this is my first lab report for Physics 2211. For the introduction and then the purpose, we sought to apply Newton's first and second laws to observe an object moving with constant velocity across a surface. This was done both with a computational model and a physical model with the assistance of Tracker. Some important fundamental principles and models to note are Newton's first law, which says that an object in rest will stay in rest and an object in motion will stay in motion unless acted upon by an outside force. This can be seen here in the expectation. As you can see, there's no outside forces other than the normal force and the gravity acting on this object, so it's going to have a constant velocity. Newton's second law says that acceleration is proportional to the force applied to an object, so therefore velocity will increase or decrease if a force is acted on that object. Again, no net external forces, so the object will continue at a constant velocity. The main result that we saw was that if the observed model, the CAN, is similar to the computational model from GlowScript, and it was similar at first, but there were differences at the end, and just a little bit of foreshadowing, this expectation wasn't entirely correct. In reality, it would look something more like this. Some key equations to note would first be how I calculated my velocity, and then also how I calculated my position. For velocity, we can assume that the net force acting on the object in the computational model is zero, and then the velocity will stay constant in the system. However, it's also important to note this is not true in the actual physical example, and this is illustrated below both in GlowScript and numerically. Second, to calculate position, we know the velocity is constant in the computational model, so then we can easily calculate the position of the model as a linear equation. Again, this is also shown in GlowScript and also numerically. For the system and in the surroundings, there was the force of the gravity, the force that the CAN exerts, and then for the observed model, the force from the initial push, and then the force of friction or air resistance. While I'm recording my video with Tracker, I pushed the CAN with an initial force. I then created a data set with the position of x direction in meters and time in seconds as my variables. I also created a similar data set with GlowScript. This one had a constant velocity and then the position would change over time. Some additional details from my experiment were that I included a glass countertop and a Sprite can. Obviously these were my system. I also included a measuring tape of 1 meter in the background for reference. I then rolled the Sprite can across a tabletop for 2.233 seconds, taking measurements at every increment of every 0.033 seconds. Some important calculations. To begin, I calculated my initial time, followed by my initial position, and then I calculated the next closest time, followed by the next closest position. With this, I could get a value for my velocity, which would then remain constant in the GlowScript code. For my GlowScript code, my first step was to change lines 16 and 17 so that I could change the mass and the radius to match that of a Sprite can. I got this information off Coca-Cola's website. For lines 35 and 36, I then changed the position and velocities to what I talked about originally with the initial equations. This way, the initial velocity will stay constant. Third, in lines 40 and 49, I changed the time in the loop to 2.233 seconds to match the tracker data at an increment of 0.033 seconds. This would mean that I would have the same data points at time compared to tracker. Finally, in lines 60 and 62, I updated the velocity and position formulas as described previously. Now looking at my spreadsheet, I have my data from both GlowScript and then also from Tracker. I inserted all of the points of time in seconds in conjunction with the positions in meters, and then collected these data points on a line graph. As seen in the graph, the points stay relatively consistent up until around 1 second. It was at this point where they began to differentiate and the position decreases from what is expected in the computational model. Again, I also included lines of best fit, especially for the actual observed model in order to show what the velocity would kind of look like. Now that we have all of our data, we can tell some key similarities and differences. So at the beginning, the positions seem to be relatively consistent for both the data sets, the observed and the expected. However, towards the end, the observed set, the Sprite can, seemed to move at less of a position than the computational model. This means that the velocity for the Sprite can would be less than the expected model. And some possible sources for this error could be that friction and air resistance might play a role, which would decrease the velocity of the Sprite can. Some important questions to ask ourselves are, what if the axes were flipped? So what if the x-axis was inverted? And the answer to this is there would be a negative trend. Since velocity is a vector, the slope would be negative. And what does all this mean? And can we predict the number of observed forces on the observed object? And the answer to this is unfortunately no. Forces such as air resistance and friction definitely do play a role, yet they can't be quantified with what we know at the moment. However, we do know that they exist, and again, this is because the model doesn't exactly match what we expected to see.